In this lecture, we will look at the EKG paper. This will be important as we move forward in learning how to interpret EKGs. Let's start by looking at the grid paper that the EKG is recorded on. This grid system is made up of two types of lines, one that is bold and the other that is not. Here we can see those lines. Here's the darker bolded line, and note how these form boxes, and here's the thinner lines that are not bold in between. And you could see that the bigger bolded boxes that we have throughout this paper have 5 small boxes going left to right and also from the bottom up. That is to say that one big box, so one of the big box, is made up of 25 small boxes. Now let's take a closer look at one of these bigger boxes here. So one of these bigger boxes is made up of 5 small boxes across, as well as 5 small boxes going up. And each small box is 1 millimeter, as you can see here, by 1 millimeter. That means that one big box, if this is 1 millimeter for the small one, and it has 5 going across, is 5 millimeters by 5 millimeters. Now when looking left to right, so going from this here, we will consider time, and when going from the bottom up, we will consider voltage. In terms of time, one small box is equal to 0.04 seconds or 40 milliseconds. And that means that one big box, which is 5 small boxes, is 0.04 seconds times 5, which gives us the 0.2 seconds or 200 milliseconds. Understanding these values can help us in determining the patient's heart rate as well as the duration of the waves on the EKG. Another thing to note on this slide are the black bolded marks at the top of the strip here. As you can see, there are, let's count them, 5 big boxes between each marking. And we said that each big box is 0.2 seconds across the top, and there are 5 here. So 0.2 seconds times 5 gives us 1 second. That is to say, the time between each black marking here at the top is 1 second. So if we look from here all the way to this end is a 3-second strip. Okay, so that's the time looking left to right. Like we said, time left to right, and then voltage from the bottom up. So if we look at the voltage going vertically, 2 big boxes, so we can say these 2 big boxes is considered 1 millivolt. So here if we look on the side, 2 big boxes here, you'll see is 1 millivolt. So let's try a quick example. Imagine we have a wave that is 10 millimeters high and 0.1 seconds wide. So what does this mean? Well, this means that the height of the wave is 10 small boxes. So we said that each small box is 1 millimeter. So if we use this, that's the height. It's 10 millimeters high. And again, this would be 2 bigger boxes. And that the width is 2.5 smaller boxes. Because we said that the width, so let's say 2.5 smaller boxes. So about in the middle here. of that. 2.5 smaller boxes, because we said the width of each small. So imagine this is our small box, as we said. The small box width is 0.04 seconds, right? And if we add another 0.04 seconds, gives us 2 boxes. Here's another one. And we said the total is 0.1 seconds. So we just have to add another 0.02 seconds. I hope that makes sense. So again, a 10 millimeter high wave that is 0.1 seconds wide is equal to 10 small boxes high and 2.5 small boxes wide. Another thing to consider is the calibration of the EKG strip. At the beginning or end of an EKG strip, you will often see a step-like structure. This is the calibration box. It indicates the standard that should be used to interpret that EKG. The calibration box that we see in A is considered our standard. Note, it is 10 millimeters high and 0.2 seconds wide. In some cases, the complexes on the EKG are so tall that they run into complexes in another lead. In those cases, we may use a half standard calibration, which we see in B. So this is our half standard calibration here in B. This is represented by a stair-like structure that has an additional step that is halfway up the standard box. So we said the standard box is 10 millimeters high. So this is 10 millimeters. And it has this step-like structure that goes halfway up. So that is to say, imagine you have a wave here in A that is like this. If we now use the calibration standard in B, which is half of that, it will have an amplitude that is half that size. So imagine if this is, say, 10 millimeters high, this whole thing will be 5 millimeters, half of it. The other calibration you may see is that depicted in C. In this case, the paper speed is increased from the traditional 25 millimeters per second to 50 millimeters per second. And the calibration box will be now 0.4 seconds wide. So here we said in the standard it was 0.2 seconds wide. In this one, when it's increased to 50 millimeters per second, it is 0.4 seconds wide. Okay, now let's look at the 12-lead EKG paper from which most of our interpretation will come from. As its name implies, the 12-lead EKG will be broken down into 12 leads or views of the heart, as well as a rhythm strip at the bottom. So as we discussed in previous lectures, we can see that here on the left we have our 6 limb leads, and on the right we see the 6 precordial leads. Okay, V1 through V6, the precordial leads. And then we have the rhythm strip at the bottom of the EKG. And as we mentioned in the previous slide, the EKG paper will often pass under a pen that is at a rate at 25 millimeters per second. And therefore, each of the small boxes will equal 1/25th of a second, which is 0.04 seconds, which equals 40 milliseconds. And as you can see here on the right side, we have our calibration, and that's at the normal standard. And between each lead, these are divided by 2.5 seconds. So each one is 2.5 seconds. And that gives us a total strip of 10 seconds. So we would have a 10-second rhythm strip shown here. So again, this is typically how it's displayed. You have the 6 limb leads on the left. You have the 6 precordial leads on the right. Again, we have our calibration here. It's often either in the beginning or the end of the EKG strip. And then we have the rhythm strip, which is very important, and it's on the bottom. And between each lead, so between and here in one, each one is 2.5 seconds, giving us a 10-second EKG strip. It's also important to note the temporal relationship of the EKG. That is to say, if we use a straight edge to draw a vertical line, which will be this red line here in the image, only the events that are touching the red line occurred simultaneously. So here's our straight edge. Everything that happened during this happened at the same time. So say we have in these leads also complexes in the middle, they were not happening at the same time. This is all at a different time. So it's important to remember that this is a continuous time as we move left to right across the EKG strip. So again, the events that happened here are not happening at the same time as here. But the events happening here are happening at the same time here. This is really important. It shows the importance of the rhythm strip. So let's first label our leads. We said we have the limb leads here on the left 2 columns. So leads 1, 2, and 3. We have lead AVR, AVL, and AVF. And then our precordial leads, we have V1, V2, V3, V4, V5, and V6. And then finally at the bottom, we said we have our rhythm strip. And then don't forget, we have our calibration here on the right side at the end. So let's imagine that these waves here in the limb leads, all these are the same. And so are the ones here in leads V1, V2, V3, as well as in our rhythm strips. And then all of a sudden in leads V4, V5, and V6, we see different leads or different complexes. If you didn't have the rhythm strip to show you these complexes, you could easily misinterpret the EKG. Having this rhythm strip will make you take into account the morphology of these complexes and thus allow you to make the right interpretation. Temporal spacing is critical in determining rhythms, intervals, ST segment changes, premature complexes, aberrantly conducted beats, and could actually save a patient's life. So make sure you have that rhythm strip when you're interpreting EKGs. So that's that one here in the bottom. Make sure that's there when you're interpreting any of these EKGs. Alright, so that's the end of this lecture in the EKG paper. Not a very long or complex topic, but one that will be very important as we move forward. Next, we will look at the basic components of the EKG complex.